Using a number of indices, we can calculate the fire burning index and identify areas that have been burnt, and also predict other areas that can be burnt, maybe in the forest, maybe in the cattle corridor. Then there is also remotely sensitive data can be used in hydrological modeling. Uh, with the use of GIS tool and remotely sensitive data like the digital elevation data, we can delineate water management, and at the end of the day, we can be able to, to calculate the statistics of wetlands within a particular catchment. And then there is also land management. Multi-sense data can be used to analyze the changes in land cover. Using remotely sensitive data, you can know different land covers, how have been changing over time. And at the end of the day, you can have a trend. For example, you can have a trend between maybe 1986, since they are available, as we said, for Landsat. This data is available from 1972. We can analyze from 1986, 2000, and 2020, and at least we can have a trend of how a particular land cover has been changing. And this can give also a decision maker a better idea of how to plan for the future. Remotely sensitive data and land management, you can also analyze the crop phenology. Crop phenology, this is how you can analyze the start and the growth of a particular growing season using using a particular using a particular satellite imagery. So when you're identifying the start and the end of the growing season, this will also bring an argument. What is the scale of what is the scale and coverage of uh, what is the scale and coverage of the area before uh, you do this analysis. Besides that, under land management, we can also know the status and the trend of a vegetation cover within an area. For example, we might want to know how the vegetation health has been changing over time, maybe within a cattle corridor, maybe within even an entire country, within the entire country. So some of these vegetation indices that can be used to track the vegetation health using satellite imagery. This may include the normalized difference vegetation index, which we know as the NDVI. There is also SAVI. This is the soil adjacent vegetation index. There is also enhanced vegetation index, that is ENVI. So all these indexes are used depending on the task and the expected output of interest. For example, NDVI will give you the general vegetation index of an area without eliminating other factors. So elimination of other factors may also depend on the additional data sets that you're going to use. For example, if you want to eliminate the soil reflectance, you can use SAVI. SAVI can be used if at all you don't want uh, uh, the output analysis of, okay, you may not want the soil variables within the NDVI. So because the soil itself can give a reflectance, and at the end of the day, you may think maybe an area with a bare soil, it has a particular type of vegetation. Maybe let me give you another example on this of soil reflectors. When you're interpreting these images, you'll find somewhere it is black, but for real, it is not black, and you might interpret it as vegetation, yet it is bare soil. So to remove all the soil reflectors, we can use SAVI. For example, you may also analyze maybe the land productivity, like what we did. Soil was also a part of the data set. So there was no use of using NDVI because it would be having to take in the values of soil. So we decided to use the survey, which is the soil adjacent vegetation index, so that it can eliminate the soil value reflectors, the soil reflectors values from NDVI. And that's how NDVI qualified to be used. Envy is usually used in areas with a number of tree covers, whereby if at all you do your analysis, you may find that the entire area is it has a higher vegetation status. Yet it is these are the trees, the tree reflectances that are misleading our output. So if you use envy, it will at least remove the canopy reflectancy.
Mr. Mugaya, I request, I think your screen sharing paused.
Yes, please.
I think your screen sharing paused and we can't see the current slides. So I request that you check it out so that we can view the slides. Thank you.
You can't see my screen?
We can see, but you paused on some slide. I think that was application of remote sensing data. That's the slide we ended on.
Yeah, that's where I am. I'm still there. I'm
Okay,
still there.
okay, please. Thank
I'm trying to to bring clearer what I've highlighted in red, vegetation status using different indices. I'm trying to bring the indices because we don't have them in the slides.
Oh, thank you very much.
Yeah. So before we land to the main core of the training, the survey, I've explained how survey came about. These are the vegetation indices. We have brought the different satellite imageries. We made an argument, compliments on the different resolution and the temporal resolution, and maybe the scale. And I showed you why we brought up MODIS. Though all your answers were okay, but the issue of the scale, very poor on a particular machine. All machines, I'm thinking they would crash. So sometimes even the equipments that you have can lead you to use a particular data sets. Any question before we start boarding? Okay, let me continue. So this I've explained at least a bit of it in the former slides. So we decided to use MODIS, as I've been saying, and it collects data on a daily basis with a spatial resolution of 450 to 500 meter resolution. We have seen this. We have talked about the NDVI and why we are using the survey. So within the formula, the survey formula, which is the ratio between the red band reflectance values and the near infrared band value reflectances, we shall add the L factor, which is the cell brightness correction. The cell brightness correction we used was 0.5. We use 0.5 because this is the commonly used value for most of the researches, and especially that are done on a global basis. But however, on the small scale, you can calculate your cell brightness correction factor and should be between 0 to 1. When calculating the soil brightness correction factor, you have to put into correction the type of soil, its organic matter, the pH, organic content, and this K factor. So this could be tedious, and besides, the accuracy may not be good. But at least a number of research that have been done, 0.5 has been qualified to be used as the soil brightness correction factor. So